okay? So you get some broad perspective of it, okay? So this was the evolution of products of our company. And I think you understand better how the multi-probe system came about. Basically, the first idea was to have an AFM that could be fully integrated into other instruments. This is a very important aspect of all our instruments. We want to make sure that they can be integrated. Okay. So the obvious thing was optics, because the company started out in near-field optics. But then, very rapidly, we went into Raman, okay, already in practically the first year of the company, and then SEM. So the first combination was this group of products, okay? But that wasn't enough, because remember, you know, when you built an AFM, and now you want to get multifunctional analysis with an AFM, because it is very good to have a system that is integratable. And in spite of the fact that there were no systems at that time, and there's still very few that can go into an upright microscope, okay? The bottom line was that that wasn't enough, because all you get is topography out of that, okay? So Nanonics had to develop a whole series of applications for multi-parameter characterization, which all of you know. One is topography, but one very important aspect are mechanical measurements. And even though with the first system, which was a beam-bound system, mechanical measurements are certainly feasible in the normal sense of the word, meaning with a silicon cantilever. Since the evolution involved having tuning forks for various reasons that I'll explain, okay, it's become very critical for us to actually implement the tuning fork for mechanical measurements. Now, I must tell you one thing, that as Professor Sahin explained yesterday, the first paper that was published on accurate formulas, okay, was only in 2004, okay? And actually, that was about the same time we entered into making tuning fork systems. So it took time to use those equations, okay, and evolve them into a software package. And this is what these gentlemen here are really doing a very good job on, because they're telling us what's not good about the software package, okay, in order to actually implement it. But it's not just implementing the tuning fork in force measurements and mechanical measurements. It's comparing it to other techniques that normal users will use. So when they go to a Brooker system or an Asylum system and they get a measurement, or they go to a DMA system and they get a measurement, you want to really integrate all of these things together and make sure that the values you get are similar. And if you don't get similar values, you want to understand why that's the case. So in some ways, I want to tell you that mechanical measurements that are made have a variety of problems associated with them. For example, I'll just give you a simple problem. If you have a thin film on top of a surface that's hard, okay, the surface contributes a huge amount to those mechanical properties. And that's not totally, if you look in the literature, there's a lot of papers done with beam-bound systems. And you have to try and understand how to relate to them even when you have these other secondary effects occurring in the system. So mechanical measurements are a work in progress in any sense. And using a tuning fork adds one more complexity, So the idea could be, why even go into a tuning fork? Because every piece of data that people have from laboratories indicate that the tuning fork should be the most sensitive method. And it has one very critical factor, and that is that you know the point of contact, which is a very critical point in these measurements. So really, without digitization, you know, the history of force measurements is that every few years, the force measurements became better and better, okay? There was pulsed force, and there was, I don't even remember all the names of all of these different methods. But their sensitivity till, I think, peak force. Peak force is the best method today that people use for mechanical measurements with AFM, but even peak force doesn't use the same probe, okay, for different mechanical measurements. So there's a whole variety of probes that you have to choose. So it's a zoo over there, and one has to very effectively integrate with that zoo in order to be able to really give confidence to people using the system that are actually working with the thing. So this is still, mechanical is still a work in progress, I would say. Optical, obviously, okay. Thermal, we have very good methodologies for thermal, and you'll see some of that today, okay. And electrical, also, good methodologies. So this is the complex, the first complex, I would say, of multi-parameter characterization of systems that AFMs can do, okay, and that our system has certain strengths in, and certain strengths, but developing strengths, rather than completely integrated strengths. Thanks a lot. Okay. So now we come to what is called multi-parameter intervention. What I mean by intervention, I mean people want to do things like the following thing. They want to put pressure on a carbon nanotube, okay? And they want to measure the Raman spectrum with pressure. That's actually a paper done with our system. For example, why is that so complicated? Because there are now other AFMs with Raman. Never mind that NanoPhotonics was the first. There are other AFMs with Raman. And the bottom line is that one of the critical factors in Raman is that the probe has to leave a free axis. So if you want to put pressure and measure, okay, you have to have a free axis. And that is very critical in terms of doing these integrated hybrid type experiments. And then there is light injection, okay, where you want to use light, and of course we're very proficient with that, and with pressure. And then heat, we are also proficient with that. And current injection, proficient, okay. And chemical writing, which is actually becoming more and more important, because there was a very large company that was based upon what's called dip pen lithography, that essentially has gone under, after maybe, I think, $150 million of investment or some ridiculous number like that. But in any event...
That's Chad Merkin's thing that
yeah,
they went under?
Yeah. So the bottom line is that there's much more interest in our technique. If you're interested, there's a very, I hope it's an interesting paper. Thank you very much. Thank you. What is the...
Paper about your writing.
What was I saying? Yes, writing, yes. If you're interested, there's a very interesting, I hope an interesting paper, that we've written for microscopy and analysis. If you cannot find it, because it's a very difficult journal to find these things, just send me an email and I'll send it to you. What is the advantage of our method over dip pen lithography is that you can do many different types of materials. And you can, for example, deposit proteins without having to functionalize the protein, okay, which is very critical for dip pen. You need to functionalize it with a self-hydral group. It really uses a spotting technique for actually putting things. If you want to hear more about that this afternoon, I'm going to speak about it, and Hisham is going to demonstrate it. I think, right, Hisham? Yes. Okay. Hisham is going to demonstrate it. So, so the bottom line is that chemical writing is something that we can really do, and multi-probe technology really can use it very effectively. So that's another group of things. But this is not enough. As we heard from Nancy yesterday, the other degrees of freedom were needed in the system, okay? For example, the first degree of freedom was simply sample scanning. The beam-bound system that we still have and we still sell is a sample scanning system. But there are tip scanning systems in the market, there are sample scanning systems in the market, but very few systems that in the same AFM have both, okay? Yes, you can put a stage from someone else. That also, everything I say can be, modulated. But the fact is that is the fact. And so the tip and sample scanning system was very critical for example, many measurements. One of them was the transport measurements that Nancy spoke about. Because what she wanted to do was to keep the sample at one position relative to an electron beam, keep the high voltage on the bottom scanner, and then switch to the top scanner and scan independently and see what the distribution of light was. And there are many cases in pump probe type experiments and things like that. That's what you really want to be able to do, okay? And so tip and sample scanning came in the MV2000 and has remained in the 4000, obviously, with more character. What do I mean by that? That brought in multi-probes, because we saw in the 2000 a problem. With Nancy, it wasn't a problem. She has her second probe. Her second probe is her electron beam, okay? But with most people, they want to inject light at a certain point. They want to pass, say, a femtosecond laser at one point, then measure carrier distribution at some other point, excitonic transfer, or all sorts of things like that are very critically involved with having more than one probe. In the 2000, it was complicated, okay? One good thing about the 2000 was, and then she used that aspect of it, was that because you can independently move these things, you can put the sample at one position, but the probe can be in another position. Okay, obviously you can scan the probe. Okay, that's also the case of the 1000, by the way. Even though you only have sample scanning, the probe is independent of any of the surrounding optics. Okay, and as a result, yes, please come. I'm going to break from. So we were here, and we had come to this point. Okay, and then this development took place about 4 years ago, and we realized that in order to achieve something like this, you needed really probes that could actually come close to one another. And the bottom line is that at that point, 4 years ago, there were no probes that were silicon probes that had exposed tips. Today, actually, there are silicon probes, and you can use those probes with our system. They're called ATEC probes. In fact, there's a type of ATEC probe called the Akiyama probe, which is a tuning fork probe, okay, which is made by nanosensors, okay? And so, really, you have the ability to go to them if you want, for such a probe, okay? Now, unfortunately for force measurements, I don't think the Akiyama probe is going to be that great, because it has a very weird oscillation methodology associated with it, okay? And it's not clear to me how you would apply the equations of Seda, okay, to that type of methodology. But it's possible that it can be in the future, but we're not putting any effort into that right now. So the bottom line is that there is the Akiyama probe, but I must tell you that the Akiyama probe is not very good for soft samples. The reason is that the Akiyama probe has a very large oscillation amplitude. You can only use the Akiyama probe with an oscillation amplitude of 1 micron, okay? So it's a huge force that you bring onto the system when you have such a large amplitude in the probe. So basically with soft samples you can forget about the Akiyama probe, okay? So the bottom line is that the generality of normal force sensing with a tuning fork is still only with these probes, and also Akiyama probes do not have any other functional probes, which are very critical for doing the type of multi-probe experiments that you see are possible. Okay, so the system, the system is actually a variety of systems. What do I mean by that? Here is the 4-probe system with 4 AFMs, okay? So each of those stars are an AFM. And here is the 4-probe system where you see these tubes coming from the left and from the right. And these tubes actually are nano-aligners. So some people would like to, in fact, inject light from the side. So let's say you have a silicon waveguide, you want to inject light from the side, okay? A nano-aligner probe would be very good there. We have excellent lens fibers. We send our lens fibers to all over the world, many to MIT, by the way, many to Intel, to IBM, because we check our surface of the lens fiber with an AFM, okay? So ours is the best, even though they're most expensive, and the ones that you get from China have, you know, the beam coming out at different angles. They're very cheap, but they're not good, okay? So really for side illumination of silicon photonics, this is a very good combination. And in fact, you see here an example, this is in Holland, where you see that only one AFM probe, and you see 2 of the nano-aligners, one to inject light into the silicon, one to collect light into the silicon. No other system has that type of flexibility. So you know that we have many different types of probes that we can provide you with. And so what I thought would be instructive would be to go and see how people have used these probes for different types of applications in the multi-probe system. So we start out with the nano-optical light source, which obviously is the Ensemble probe, and an AFM. And there's a paper now published in NanoPhotonics, okay, that should be very interesting. One is an AFM probe, and one is an Ensemble probe. For example, we saw in Juan Merlot's talk yesterday that he had taken the AFM with the with the Ensemble probe itself. Ensemble probes have the capability to do AFM, but I would say they're compromised AFM because the size of the probe is convoluted with the structure. And so you don't really see the same type of fidelity as you see with an AFM probe. So in this case, they used a glass probe for AFM, an AFM-based probe, with one probe, okay? And they obtained images of these tubes, these fluorescent tubes. And then they were able to go to a particular tube, okay? And then they could focus down on a particular tube within that structure. So you see, for example, I don't know if this works. You can see, for example, in this structure, here, for example, this is fluorescent. This is less fluorescent. One big advantage of this method for fluorescence is that you don't have to search for the probe with, search for these structures with your N-SOM probe, okay? So you know exactly where they are. The two probes are very well correlated. Why? Because you can really bring those probes in contact with one another. There's a paper in the literature based on a group in Germany who have a multi-probe system. And they showed that the feedback of one probe is affected by the feedback of the other probe when they're in close proximity. So you know that the probes are very close. So Hisham will show you that today, I think. Right, okay. So the bottom line is that, that you can really bring these probes together. And so the bottom line is that you can find the sample, you know where the things are, then you can go with your N-SOM probe. Why is that important? Because if you're searching with an N-SOM probe, you're shining light on this material also. And every time you shine light on the material, you bleach the material. So there are many big advantages to actually being able to know your field of view and where the actual sample is, and then to rapidly bring your N-SOM probe onto the region that you want to actually look at. And here was another example, okay? And I don't know why it's flipping, but never mind. That's, here, you see this? This is here, okay? And so you see very effectively, in fact, but this guy here is not very fluorescent.
It's the one to the right.
It's the one to the right? Excuse me. Oh, I'm sorry, it's this one. That one is this one, I think. Yes, that's right, I'm sorry, excuse me. Thank you. So, so the bottom line is that, that you get the AFM of the tube, and you get the N-SOM profile of the tube, okay? So you can see this is 0.2 to 0.4 microns. So this is 200 nanometers. So this is about 100 nanometers, this profile here, okay? In fluorescence. Now this is Nancy's data, actually. I think you took this data, right, Nancy? Or did Hisham, you took it? Who took it?
It was a joint effort.
Joint effort. So if if I say anything wrong, just correct me, okay? From what I understand, there are two semiconductor crystals over here, and in between is sitting a protein which is fluorescent called phycocyanin. And the idea was to see if there would be transport of, I guess, carriers or excitons or things like that through the phycocyanin, okay? And what you see is in the AFM, you barely see the phycocyanin because it's very, very low topography. And these things are basically dominating the image, which they're much higher topography here. So what you see in fluorescence is that you see fluorescence all along this region between these two systems. In this case, the actual experiment was putting a probe over here to excite and another probe to collect, okay? So this is a case of like, not a pump probe, but an excitation at one point and collection. So instead of using an electron beam, using an optical beam. And one of the first experiments that was done with the very first multi-probe system ever, okay? It was a previous version of the system that we see now, okay? We called it the 3000, but it was a previous version. But this gentleman, this Stillaci, I think his name is Stillaci, was very intent on getting it, okay? So he wanted to do this experiment, eventually did do the experiment, okay? But it was the very first system, okay? And, but he got very interesting data even at that point, because we knew very little about multiprobes. And that was that here is a probe injecting light onto a plasmonic waveguide, and another probe scanning. And in fact, he was even able to see the second probe. He scanned over the second probe, okay? And here are zooming in of the injected light and the distribution of the plasmonic propagation. And what you see here, this is the point of injection, and this is the point of plasmonic propagation. So both in terms of plasmonics, in terms of fluorescence, okay, this is a very important development. And he was even able to see something very interesting, and that was that he was able to see the decay, which was with quite high resolution, because he was able to bring the probes very close. And he saw a beating, and the beating was between the two probes. Both probes were metallic probes, and the light was beating between them as the probe was scanned. So this was actually, you could call it something that was connected to the experimental arrangement rather than the actual data itself. But here is a very nice study that was done much more recently, okay, many years later, okay, and that is that you use one probe, okay, to illuminate at different positions in this plasmonic structure. Now you must understand something about ensemble probes. Ensemble probes give all K vectors. So, you know, if you want to excite plasmons, you usually need to take far-field light and get the right K vector in order to generate the plasmons, okay? But you can't do that without having, let's say, a coupling grating or something that you have to fabricate into the system. And you can't do this anywhere. With an ensemble probe, you can put the ensemble probe for illumination anywhere along the plasmonic structure, and then collect the light, okay, at different positions. And you can see, depending on where it is in the plasmonic structure, the distribution of light is totally different, okay? And this is calculations over here, okay? So, in fact, what the customer said, the perfection of the experiment is benefit from the use of the ensemble probe to excite the sample in the near field. This point surface plasmon polaritron source can be used in many areas for its high coherence, deterministic position, and minimum requirement for the initial light source. And this is exactly the case that we have over here. There's someone at the door, I think.
Nothing used for that.
Yeah, and this paper was just published. This is a very interesting paper. This paper was a group in Sweden, okay, that was working with Lego. And Lego today uses 72 different colors. And they want to replace their colors with nanostructured surfaces, just like a butterfly has color because of its nanostructure in its wings, okay, and not because of some dye it has, okay. You have nanostructured materials that can give you different colors, and this is what Lego is trying to do, but they want to investigate it, and so they are using two probes, one to excite and one to collect at different regions in order to investigate the structure itself with this group in Sweden. And so you can, in fact, bring two probes into incredible close distance, okay? This is one of the first things we did, and you can see what this means.
stop.
Good stuff. Yeah. So when you bring a probe close to an ensemble probe, you change the boundary conditions and more or less light comes out of the ensemble probe. So you can see this was a very early experiment that was done by Hisham. So this is nano-optical characterization and also multi-probe plasmonics. So this is what was the first part. The second part is a nano-optical light source and a nano heater. Okay? For example, people are very interested in understanding the distribution of heat in optical structures. This is what is called a quantum wire laser, where light is confined in this laser, okay? And you can look at the optical distribution of the mode. The difference between this and this is 0.8 nanometers, not 0.8 nanometers spatial, 0.8 nanometers in wavelength, okay? So the mode structure has changed of this laser. But what people really want to know is how does this distribution of light, how is it connected to heat? So you can use one of our thermocouple probes and look at the distribution of heat and compare it online to the distribution of light. And what does that mean? It means that you see there's very little difference between, there's very little correlation between this and this. You see here a bowing towards the P contact, and that is the reason for the heating, okay? And not the distribution of light in this system. Now, nanothermal characterization. So, nano pipettes and nano heaters. So, what was done over here was a nano pipette was used to place carbon nanotubes across a junction of two nickel pads. So this is a nickel pad, this is a nickel pad, this is the junction, and a carbon nanotube was placed across it using a nanopipette, and then two probes were used. One for doing heating, and one for using it as a thermocouple. So one of the probes is sitting here heating the carbon nanotube area on the nickel pad, and this is the AFM, and you see that in the region where it's attached to the nickel pad, there is very hard for it to compete with the heat conductivity of the nickel pad. Only in the region where it's suspended do you see the heating as shown by the yellow color propagating along the carbon nanotube. So these are very important experiments in heat transfer which can be done. And people are very interested in this type of multi-probe measurements. Also, you can do electrical measurements. This is a 32 nanometer transistor. And a group in Berlin has actually been able to use the system to deposit a carbon nanotube across a contact and to see the carbon nanotube in terms of the deposition. This is a SEM. So you only see the conducting carbon nanotube. Here there are two, both a conducting and a non-conducting one. You see that the height is 1 nanometer here, okay? And these are the measurements, okay? This is with the tube, okay? And this is just, I'm sorry, excuse me. I'm sorry, this is, I think that this is, it says the red is on the wire and no tube, and this is with the single tube. I'm pretty sure I'm right, okay? And this is with a bundle of tubes, okay? Some of them semiconducting, some of them conducting. So now we will talk about silicon photonics, okay? So if you want to introduce light from the side, yes, very soon, I'm nearly finished.
Okay.
Introduce light from the side, okay? And then you want to look at the evanescent field, okay? You can do that by scanning a probe on top. So you're injecting from the side, and you're scanning a probe on the top, okay? And then you're able to look at the structure and the evanescent field. And then if you want to look at the profile, or you want to collect light, or you want to inject light from the other side, okay, you can see that you can use a straight probe. This is important for you, by the way, because a straight probe could be very important for the sidewall that we're talking about. And of course you can get the profile, etc. So that's silicon photonics. And people have even used nanopipettes, but I won't go into that right now because we'll talk about that later. And finally, and this is the pinnacle of our development right now, and that's why we're putting so much effort into all of these other, like the force measurements and things like that, because we really have a portfolio of very differentiated products right now, and we want the user to get the most out of that. Okay, so the last system that was in the plan, and it's now actually there are already 3 systems in the market. Okay, they were sold within the last year. Okay, is a cryogenic down to 10K system for things like molybdenum sulfide, tungsten diselenide, graphene, these type of measurements where you want to combine optical, electrical, photoconductivity, electrical measurements. You want to connect them with Raman spectroscopy, maybe with other spectroscopic methodologies, maybe lifetime measurements on molybdenum sulfide, those type of things. And this system can have up to 3 probes, okay? And the temperature that you can achieve is 10K. Actually, we've gone below 10K, but that's the value that we give. And it's a very, very, very interesting system, I believe, and it's connectable fully to Raman, okay? And I think that it has lots of utility, and it has many of the aspects that you'll know in the multi-probe system, and we really hope that it will be very effective. In any event, so with that, I think we'll stop, okay? And